Alright, 1 2 1 2 1 2. Check the cameras are working. Whoa! We are zoomed in on that one. Screen. Yeah, I think we're good to go. Let's make sure that we're live streaming, and we are currently live. Alright, what's going on, gents? Now, I know this is a really random time to be streaming. It's currently like 9 AM here in the UK, but I want to get this finished, and I know that my live stream I did yesterday, quite a few people were invested in what I was doing and what the solutions to some of these design flaws were. So I know that this stream isn't probably going to get a lot of views at the time, but I'm hoping that, you know, you'll be able to watch this back after it's finished at a later date when it's convenient to you. So I'm just doing this stream really so I don't have to make a video because that takes time, and I can just stream while I'm doing it. So as you'll remember from part 1 of this stream, we identified the design flaws with this amplifier. If you're not familiar with those, then go watch that stream, it's really interesting. And we started tackling the issue surrounding the parasitic current draw when the amplifier is connected to a power source but not powered on with the remote cable, and also the strange voltage regulation behavior where it would kind of go into 2 different power modes, but it seemed backwards to how you would normally want to do it. So I'm just going to connect these wires back up, and we're just going to continue with that. So on the end of the last stream, what we did was we were playing around with some different resistor values by the MCU here, and these resistor values are a voltage divider that was allowing the MCU to detect how much voltage is at the power terminal. So this is the MCU, and there are some resistors around here that are stepping the 12 volts down from the power terminals and allowing the MCU to see, you know, how much voltage is on there without actually being sent like 16 volts, because this MCU, its VCC is about 5 volts, so we don't want to be sending 16 volts to any of its input pins. Now, what I discovered late last night or this morning or something is that in order to get this, so this is really strange, and I don't know whether this is intentional or not, but basically when you have a chip like this, where its power voltage, you know, it's the voltage it uses for power, in this case it's 5 volts, none of the other voltages on any of the input pins, you know, that the chip is using as like data inputs or reference inputs, none of those should ever really exceed the supply voltage, okay? Because, I don't know, like when you look at the data sheets, it will say maximum reference voltage on any of these pins, VCC plus 0.2 volts is the like absolute maximum that you should ever run it at. But in this case, it's not. The way that this amplifier is running is it has 5 volts VCC, it's actually about 4.9. But the reference voltage on this top pin up here, which is the input it's using to read the voltage on the battery terminals, it actually rises to like 5.6 volts. And remember that this amplifier has 2 different modes of regulating the power supply, 2 different rail voltages that it will kind of lock into, and we discovered that it locks into the first rail voltage from about 9.8 volts worth of voltage on the battery terminals, and then it sticks at 151 volts worth of rail, and then when we increase the voltage beyond 13.5 volts, it then switches to the higher voltage regulation mode on the rails, and it allows up to 195 volts on the rails, and it locks it there. So it's kind of got 2 modes, and the reference voltage on this pin that's required for it to switch into high rail voltage mode is actually like 5.2, 5.3 volts, which is above the VCC supply of this chip. So that it's the first time I've ever seen something like that be implemented, or I don't know if that's intentional or what, but it doesn't really sit right with me. It doesn't kind of make a lot of sense. So what I want to do, as I explained yesterday, is we want to lock this amplifier into just one of those rail voltage modes, and then calibrate the regulation voltage that the rail sits at using the other voltage divider over here, okay? But then this is how the MCU is reading the rail voltage. So we have the rail voltage sense here and power supply terminal voltage sense here. So first thing I'm going to do is I'm going to lock this chip into regulation voltage mode 1, which typically was 151 volts worth of rail. We're going to lock it in there, and once we've got it locked in, we'll then adjust the values of this voltage divider so that the regulated rail is up at maybe like 180, 185 volts, something like that. So let's get the hot air gun cooking and get some flux on the board and do that. How's everyone today? Like I said at the start of the stream, I do not expect this stream to have huge viewership at the time. That's not the intention. The intention of this stream is just to create a basically watchable video playback later, so that people can catch up on what happened with this amp. How's it going, Brendan? How's it going, Andy? How's it going, Tony? Amir? Yeah, good to see you guys. Yeah, the B2 Riot 16K, terrible board. The B2 is a Chinese copy of this sound digital clone. This is a Korean, so it's the same. It's the same circuit that's been cloned, but this one's been done in Korea, and it has a bunch more issues than the Chinese ones. So if you're going to get a clone of the sound digital circuit, even though they suck, I would still recommend the Chinese one over this. This is absolutely dreadful. Hawaiian is probably not going to be a short stream, but like I said, this isn't intending to be a stream for you to watch now. This is one for people to watch back later when it's convenient for them. So Amir, definitely do not put your money anywhere near any of these circuits. Any board that looks like this, stay away from it. They're absolutely dreadful. If you need something that's this much power from a single board, your best options are going to be a PowerUs PW15K 1 ohm version, or maybe a Taramps Base 15K is quite nice as well. Not quite as good as the PowerUs, but still pretty good. I think Taramps are getting quite close to probably coming out with the Smart. Are they going to do a Smart 12? I don't know if they'll do a Smart 10. They've done a Smart 3, Smart 5, Smart 8. I think the next one up makes more sense to go with a Smart 12. I'd be surprised if they do a Smart 10. It's kind of too close to the 8. So I feel like 12 would be the most sensible jump to do. So we're just modifying the voltage divider here so that we have about 3.8, 3.9 volts on the reference pin for the MCU to take as the battery voltage. And yeah, we've shifted over the supply voltage for that divider from being the battery terminal, which is on this pin here that we've now lifted, because obviously that's going to fluctuate with our input voltage. We want a fixed voltage reference so that it stays locked in. So we've tagged it onto this little resistor next to it, which has actually got VCC for the MCU on it, which that's 5 volt ref. So we've just stepped it down to about 3.8 volts there, and that will lock it in at a fixed voltage reference so it stays in the same mode. Get rid of the flux. There's quite a lot on the board here now. There we go. Alright, so let's just confirm that that has locked it into the stage 1, the first stage of regulation, and we're never going to see stage 2 again. There's no need. We only need one stage of regulation. But it's cool that it has 2 stages, I guess. I guess you could, like I said in the previous stream, you could fit a switch or a potentiometer and have it running in like daily mode at like a low rail voltage, and then switch it up into mode 2. So yeah, let's turn on the power supply. So what we want is to see about 3.8 volts there on the scope, something like that. Okay, well, we've got 4.8 volts there, which is more than I probably intended. Oh no, sorry, that's the VCC, my bad. I was probing the wrong point on the board. Here. We've got 3.7 volts. Yeah, that's probably going to be enough. Let's just see what mode that locks the amplifier into. I hope that that's going to be high enough that it's not going to sort of trip into low voltage. 3.7 is a little bit lower than I wanted. So I could probably go down to 1,000 ohms. Actually, I'm going to drop that down a little bit lower. I'm just going to... I've got a 1500 ohm resistor in there at the moment, so I'm just going to drop that down to 1000, and that should just bring the voltage up a little bit. I kind of want to see around 3.8 to 4 volts there. There we go. Yeah man, this live will be saved to watch later. That's the intention of this live. This live isn't going to get many views just now, and I understand that. So the intention of doing this live is just so that people can watch it back later when it's convenient for them, because it's a random time to be streaming. Do new amps use microcontroller plus DSP for Class D modulation? All the other ones I've opened up use fully analog. Yeah, no, basically I haven't really seen any that use the microcontroller for anything Class D related. The microcontroller in the ones I've seen just is used for protection circuitry and to generate the pulses for the power supply SMP. So yeah, none of them I've seen actually control or generate anything for the Class D side. It's all just, yeah, self-oscillating, or yeah. Alright, so we should now have about, let's have a look, maybe like 4 volts there. Yeah, 4 volts, that's perfect, that's what we want. Okay, now we've got 4 volts on that reference pin. That means that this amplifier is now going to be locked in at the first regulation point, which is what we want. So if I just move this round, get the camera changed slightly, so let's knock that over. So now we're going to be looking at this voltage divider over here, and this is the one that the MCU uses to sense the rail voltage. So currently it's regulating the rail at 151 volts, and we want it a bit higher than that because that's a bit low. So I'm just going to attach a load to the amp terminals here, and we have at the moment, just make sure there's no rail voltage on here. Okay, we've got 30 volts in there at the moment, which is a little bit spicy. So let's just get that dissipated. There we go. So the voltage divider we want to look at. Why is my scope cam looking different today? There we go, that's a bit better. So the voltage divider we want to look at is like this one, like I said. So we have rail voltage on, I think it's this resistor. So this resistor is directly connected to the rail, there we go. So we have our high voltage rail on this resistor. It then passes through this one. This one is a 124. Okay, and then after this resistor we have it going into R71, which is a 473, and then that goes on to the MCU, which goes into this pin right here. But obviously after this resistor we will probably also have a pull down resistor, which is this 102 here, and this is obviously going to be pulling that down to ground, allowing the voltage divider to work. So what we can do is modify the value of R71. We need a higher resistance there. So at the moment we have a 473. Okay, we can either increase the 473 or the 124. I think the 473 is going to be the one to increase. So what we're going to do is remove that resistor and replace it with a potentiometer for now. And then we can calibrate what kind of resistance we need in there. We can actually use that, just might be interesting for you guys if you want to have a look at this. We can actually use a calculator to work this out. So if I do voltage divider calc, bring up the screen for you. So if we have a look at a voltage divider calculator, we basically have our resistors here. We have R1 and R2. Now we have 3 resistors, but that's just basically because we've got 2 in series. So R2 in this case is going to be the 102. So that's 1000 ohms. I'm actually just going to change this to kilo ohms. 1 kilo ohm. And for the 2 series resistors, we have 124 plus a 473. So that is 1, 2, 1, 2, 3, 4 plus 4, 7. So we have 167k at the moment, and our source voltage is, well, 151 volts. So the output voltage is 0.899 apparently, according to this. So if we want 180 volts here, okay, will it tell us, oh yeah, no, we want the same voltage there. Will it tell us what resistance value we need here? Okay, so we need basically 200 kilo ohms, according to this, in order to hit the same reference voltage there, across the output. So we basically need, yeah, we need a 20 or 204. Yeah, a 204. Something along those lines, maybe a 224 would be fine. Let's get rid of that and let's go for 185. Yeah, so basically around 200 kilo ohm is what this is suggesting that we need in order to regulate at about 185 volts. So let's see what I've got. I will have to be able, obviously I've got 2 resistor pads here, so I can make that. So I've already got a 124. So I've got 120 ohms or 120 kilo ohms already. So I basically need, in order to make that up, I need yeah, I need an 80k. So I need something like 80k. So 803, 86, something like that. So let's see what we've got on donor boards and stuff, because I don't think I'm going to have any resistors that are that kind of value just laying around. So we want something that begins with an 8, ideally, and has a 3 at the end of it. And we can obviously make the resistance with a couple of series ones perhaps, or if we find something that is a big enough resistance on its own, that will also work, like the 224 or something like that. What do we have here in the voltage divider for this one? Let's see if I can clean this up a little bit so I can see the resistor values a bit easier. 563, that's a little bit low. 563, 563, 103. So we'll also 563s. Not seeing anything quite high enough yet. 273. .683, that's closer, but we're about 20 kilo ohms off. So, okay, I'll bear in mind that there's a 683 there in case we want to series a couple of resistors together. Then we need a we need a 20k. Alright, okay, that's worth bearing in mind. Let's have a look on the tower amp stoner board, see if there's a resistor value on here that will work. Morning Matt, how's it going buddy? Thanks everyone for joining this random timed live stream. We've got a 104, so we've got 100k. I could series that with something higher, perhaps. We've got a 104, 231. Uh, 1503, that's getting close. 1503, that's 150k. So with 150k, we would just need another 50k, 47. So if I do a 1503 here, then I just need a 473. Is there going to be a 473 anywhere? Seems like a relatively standard value that you might find. I don't remember seeing any. Maybe a couple of 104s. A couple of 104s in parallel giving me 50. So I can see one 104, but can I see another one? If I can see a second 104, then that's what we'll do to make 50. Oh yeah, okay, I've seen it. Right, okay, here's what we do. So for the voltage divider, we use a 150k ohm. Then, on the second resistor pad, we use a pair of 100k's in parallel to give us 50k. Alright, let's try that. So let's just pop these to the side for a minute, nice and safe. There's our 124, our 473. Okay, now let's grab these from the tower amp stoner board. Got a 150k to start with. This is a very high thermal mass trace, this one, where this 150k is. Come on, off you come. Off you come. There we go. So we're just going to plop that one there as the first step down. A little bit of flux because it seems a bit dry. Okay. And then we're going to stack a pair of 104, which is 100k, and that will give us 50k. I once rewound the transformers, upgraded the output side MOSFETs for higher voltage. It lasted a couple of months and then ended in a smoke show. A smoke show sounds like power supply section failure. So yeah, your limiting point was probably the power supply transformers saturating. Removing surface mount resistors from these Terramps boards takes a while because the solder they use is like lead free and the boards are very high mass. Right, so we're going to drop 104, just like that. And then I'm just going to grab my solder wire to add some big beads so that another 104 will sit on top in parallel. There we go, there's some beads. Put some flux. Grab the other 104. Haven't been able to catch you live in almost a year, been busted up. Oh man, I'm doing well, thank you. Whereabouts are you based? It's a random time that I'm streaming today. I'm not really expecting there to be many viewers this morning. It's like 9:30 in the morning here in the UK. But I'm mostly doing this just because I wanted to get these mods done. But I know a lot of people were invested in the solutions to these mods and what the outcome was. So I thought I'd just stream it now so people can watch it back later. Yeah, what have you been up to, man? There we go, a little stack of paralleled 104. I wonder whether that calculator was accurate and whether that's going to just work. So I'm looking for a regulated rail voltage somewhere in the 180, 185 region. I don't really want to go any higher than 180, 186, 187 if I can avoid it, because it's a little bit high, a little bit close to the 200 volt breakdown limit of these parts. So let's power it up and see, shall we? Okay. So let's probe the rail voltage here, and as before we're going to start off super low down on the voltage. We're going to start down at like 9.3 volts just to slowly increase the rail voltage and see where it starts to regulate. I don't want to overshoot 200 volts and end up killing some parts, so we're going to start off super nice and low and go from there. It takes ages to power up this amp. It has a very long health check. Okay, there we go. We're up and running. Rail voltage is currently sitting at 143 volts. Okay, so we've got 143 volts on here, so we're going to increase the power supply voltage here and see where we start regulating at. Okay, this is good. We're already above the 151, 165, 170, 175, 180. Okay, there we go, 182. That's our regulation point. So now you can see if I go all up to 14, we're not going above 182. That is pretty much exactly what I was looking for. Amazing. Now, one thing I do want to check is I just want to check that when the amplifier is powering up through its health check, it isn't kind of freewheeling beyond 200 to start with, and then when the Class D initializes, it kind of sinks back down. So I'm just going to kind of let the rail voltage just dissipate for a minute, and then I'm just going to power it back up again with 12 volts going in. I just want to make sure it doesn't kind of overshoot and freewheel. Broke my back or re-ended on the highway. Oh man, that is absolutely brutal. Jesus, I'm so sorry, man. Yeah, that's one of my biggest fears actually, is having to come to a stop on the like the motorway, the highway, and having people behind just not stop. Yeah, that sucks. I'm so sorry, man. That's fucking horrendous. I'm always so conscious of that. Like, if ever like traffic is coming to a stop on the motorway, and I notice it, I'll firstly try and get in the inside lane, like, you know, close to the hard shoulder. I'll come to a stop and I'll just be constantly looking in my rear view. And if it looks like some car is hauling ass towards me and like doesn't look like it's slowing down, I'm pulling out. I'm going down the hard shoulder for a bit, just getting out of the way. I'm so conscious of that. Yeah, no, that sucks, man. Possibly an unpopular opinion, but I am massively in favour of full self-driving world. I honestly am fully in favour of everyday traffic, people going from A to B, people going to work, people going to see their family, taking their kids to school. Your average everyday journeys need to be automated, because yes, computers will make problems, there will be errors, there will be glitches, there will be things happen and crashes will occur, but there'll probably be about 0.2% of the crashes that currently happen due to human error. Human error, making the wrong move, not seeing a car, being distracted on your phone, talking to somebody, having a health issue, having a heart attack, passing out, falling asleep. Humans cause crashes, absolutely monstrous amounts of crashes. Computers have problems and will cause crashes, but it will be so much rarer than human error. And I agree, I love driving, it will suck. Like, yeah, I'm fully prepared, I'm fully aware it will suck. It's going to be so boring. I love driving, I love knocking through the gears, like I love driving my manual car, I love driving the Proton, but the way that I describe this to people, if you have yourself, or if you know anyone who has lost a friend or family member in a car accident, if somebody from the future came to you and said, oh hey, by the way, we can bring that person back that you lost in exchange for never being able to drive your car again and having it all be automated, would you take that exchange? And I guarantee 100% of people who have lost a friend or family member through a car accident would take getting their friend or family member back over being able to manually drive their car. So when we go fully self-driving and fully automated in the future, which is probably going to happen, lives will be saved. People will live that wouldn't have lived as a result of everything being self-driving. And unfortunately there will be people that unfortunately pass away in car accidents caused by self-driving cars having malfunctions. Like, yeah, that is going to happen, but I think that it's going to be on the scale of aviation crashes, like plane crashes. Plane crashes happen. Aviation is the safest transport institution in the world. If you want to get from A to B and live, you get on a plane. That is the safest way to travel, bar none. Like, maybe trains are close, but aviation is the safest way to travel. But stuff does still happen, like random edge cases, random stuff that no one's thought of happens, and plane crashes happen. So yeah, you will get crashes with self-driving cars, but they will be they'll be as rare as plane crashes, hopefully. Yeah. Anyway, 12 volts. Let's see, hopefully we don't overshoot 200. No, we stick up there at 180, 181. Yeah, perfect. Amazing. That is precisely what I was looking for. I mean, the Class D switching looks like it's off the screen, but I don't think it actually is. I think it's just something weird with my oscilloscope. So yeah, I'm happy with that. That is good. So we have fixed two of the strange design flaws or choices. We fixed the parasitic current draw when the amplifier is connected to the power terminals, just by taking a different reference for the battery voltage, and we have fixed the weird issue where it goes into a second high power mode at high voltage, which doesn't make any sense. As a result of this quick mod though, what we have unfortunately lost is we've lost low voltage protection. So this amplifier won't go into protect anymore when the battery voltage is 8 volts or something. It will still be running and trying to run. So that's unfortunately a side effect of this quick mod. We could do all sorts of other much more complicated modifications that retain the probably retain the low voltage protection somehow, but that's going to involve adding lots of other circuitry here to give a sort of floating reference from the power terminals that activates with the remote, and then doing something else with the voltage regulator to keep it locked in. So this is the quick and easy way to fix both of those issues, just by changing a couple of resistors over here in the voltage divider network. Now, the last thing that we've got to fix on this is the absolutely awful power supply optimization over here. So as we saw in our first live stream yesterday, there's either an issue where there's not enough dead time between A and B pulses on the power supply for the FETs, and as a result there's humongous cross conduction, or the frequency is incorrect for these transformers. Now, if the frequency is incorrect, there's not really much I can do about that. I mean, I could retrofit a TL494, but that's pretty major. And I'll probably say, you know what, we just have to leave it, and yeah, the power supply will get warm, and it sucks, but this is how it is. The alternative is changing the transformers. I could change the transformers, so I do have I do have like a couple of donor boards that have transformers on them that, you know, would probably be correct. So the power supply switching frequency of this is, I think it's like, what was it, 25 kilohertz, something like that, which is the same as what these Sundown SFB and the DefBonce donor boards I've got was, and those didn't have this issue with the power supply. It was fine, there was no cross conduction or ringing on the transformer, but there is on this one. So yeah, if the transformers are incorrect, I could strip the board down, change all 6 transformers, and that might fix it, but it might not if the issue is dead time related. So I've just got to kind of choose an issue that I think it is, and try and fix that and see if I got it right. That's the best way. William says self-driving cars will encourage lazy drivers. Well, that's the point. I'm talking about fully automated. When everything's fully automated, there are no drivers. You don't drive. You know, you don't get on a plane and say, oh, this passenger's a lazy plane driver. He's not driving the plane because he's a passenger. When the world is self-driving, fully, everything is automated. I'm talking like 20 years probably in the future, maybe even longer. I'm not talking about a little bit of self-driving on the motorway. I'm talking about you get in your car outside your house, you sit in the back, you go on your laptop, you do your work, your car takes you from A to B, regardless of what road it is, whether it's a side road, a main road, a back road. I'm talking literal automation. So you're not going to be driving, there's no laziness, you'll be allowed to sleep in your car. I'm talking that level of automation. That's when lives will be saved, and yeah, I'm actually looking forward to that world. I hope I live to see it. You can be as lazy as you like because you ain't driving. That's like saying you're a lazy bus passenger. Like, what difference does it make? So in order to see what the issue is on the power supply, like I said before, we either need to change the transformers and see if that sorts it, or we need to modify the gate drive circuit. And I think that's what we're going to do. We're going to do the gate drive method. So if I do these top ones, probably that's going to be easiest for you guys to see. So my guess is that there's not enough dead time. And I wonder actually, are there any MOSFET drivers in a SOIC 8 package that are 2 in, 2 out and have a programmable dead time? I doubt it. I'm just thinking whether I can change the 44. It's got a 4427 driver. Let me show you this camera. So, oh, it's not very bright, is it? Why is that so dark? Hang on a minute. Right, let me just change the settings on this camera a little bit because it's so dark. Configure video, is that going to work? Here we go. Okay. Gain. Let's increase the gain a bit. Brightness. There we go. A little bit more brightness, please. It's so reflective, this board. Makes it very difficult to see stuff. So this right here, this is the MOSFET driver. This is a 4427. Now I wonder whether there are other MOSFET drivers that just by nature have higher dead time, like just by how they operate. So I wonder whether I can swap out the 4427 for something with just naturally higher dead time. That would be a much quicker, easier way to get rid of the cross conduction on the power supply FETs. The other option is to go over to the power supply FETs over here and to increase the value of the gate resistor. We've got 10 ohm gates at the moment, so I'd possibly increase to like 47 or maybe even 100 ohm gates, but I would have a parallel 4148 diode so that the turn off is fast. So we can slow down the turn on and speed up the turn off, and that will give us kind of force there to be a bit more dead time between bank A and bank B turning on and off. So yeah, not really sure. Maybe should we have a little look, just because we got some time, should we have a little look on the interwebs and see what kind of dead time we're looking at for some of these drivers? So let's have a look on the interwebs. So we've got IRS 4427. Was it? Oh, no, it's a 4227, is it? No, there we go, 4427. It's an S, 427S. Hey everyone, just wondering, you just had in your hands a donor board, and how come there were too much to fix? Well, when the board looks like this, no one's really going to want that or run it. Like, this is repairable, don't get me wrong. It's just traces. It's just a bit of, a bit of PCB board and traces. You could rebuild the traces on that, and you could fix this amp. But no one's going to buy that. No one's going to want to run that. Like, people that don't understand electronics and look at that, and be like, that's a mess. It's been on fire. Like, there's so much I'd have to change. The repair cost for me to repair this would be greater than just getting a new amp, probably. I'd have to charge a lot of money to fix that, so not worth it. How's it going, Simon over 2, my man? Good to see you, buddy. Morning. So yeah, we were looking at dead time differences on these drivers. So what is the quoted dead time or whatever on this thing? Oh man, I hate it when I do that. Take me to the PDF, not the freaking website, bro. What are you doing? Oh, that's one we had before. This is the PDIP rather than the SOIC, but I'm sure it'll be the same. So time on, T on and T off. So time on and time off is 50 nanoseconds. Now if we want more dead time, do we want that to be faster, possibly? Does it mention dead time anywhere in here? No, so dead time isn't mentioned in here. And that kind of makes sense. It's just a MOSFET. It's just a very basic buffer driver. It's not going to have any kind of dead time that's programmable or anything, or that's intentional. It's just going to be passing on the pulses that it gets from the from the source onto the FETs. So Sub Dynaman, what's up, buddy? Yeah, this is a very random time for streaming. I appreciate that. Like I said earlier, I wanted to stream. It's 9:50 AM here in the UK. I just wanted to stream this because people were wanting to follow this kind of video series of this amplifier, and I needed to get it done this morning. So I just wanted to stream this morning, get it done, and people can watch it back at a later time when it's convenient for them. The audio pipe modification is done. I just need to mount it into the heatsink. I need to drill some holes in the heatsink and stuff. Haven't got around to doing that yet. But yeah, the audio pipe mod's all done. Just got to do some drillage and screwage into the heatsink. So yeah, I don't think that changing the driver is really going to make a difference. Turn on propagation delay. I did have an instance one time where I swapped the drivers and the pulses were like on the edge of cross conducting, and the new driver that I fitted caused there to be a bit more cross conduction just because it was either faster or slower. I don't know which way round it was. So I know that changing the driver can impact cross conduction just based on its timings of how the driver is working. But I don't know which way around it was, and I don't know if I've got any drivers that that might be better suited. I've got some 4427s that are a different batch. This is a 4427 currently in the board, so I don't think changing that's going to make a difference because they're both the same model. If I have a different model of driver, I might fit that and just see what happens. See if it like makes the idle current more or less, then that will just tell us a bit about what's going on. If it changes the idle current, if changing the driver changes the idle current, then we know that the issue is dead time related rather than switching frequency related. So that might be a good little first test to do, just to double check. A lot of these drivers I've got in here are actually inverting type because I ordered the wrong type quite a few times. So I think a lot of these are accidentally inverting type drivers. We've got a 34151. What's that? Can I use that? 34151. Let's have a Google of that and see what we get. So the 34151, baby boy. Four. Is it going to tell me which one's inverting and which one's non-inverting? Right, so the MC34151 is a dual inverting. Okay, that's no good. So we can't use that. We need non-inverting. Okay, we've got one here that's marked C2. This is going to be from a Chinese clone. Alright, so let's try fitting that and just seeing if there's any difference. I think that might be a UCC part perhaps. So we can fit that and just see whether the idle current draw is any different. Yeah, all of these are bloody inverting type. Not good, not what we want. What projects do you have in the near future? So, projects that I have that I'm working towards, I've got a few. Project number one, obviously, is Boom or Bust Season 2. I need to drive like a flipping 6-hour round trip in order to get the PT Cruiser that I want to use for Season 2. So that's kind of what's stopping that from happening at the moment. It's a long drive just to go and get like a bloody PT Cruiser remote control car. So I'm trying to like get that journey mixed in with going that way for something else, so it doesn't feel like a massive waste of my time. But maybe I'll just do it. So yeah, Boom or Bust Season 2. For Boom or Bust Season 2, I actually also need more space. I need somewhere to have that setup permanently set up. And like for Season 1 I was using the dining room, and then I started using the workshop, but I don't have enough room in here to set up for Season 2 for what I want to do. So for Season 2 of Boom or Bust, I need a space. I either need to build a shed in the garden, or I need to rent a little office somewhere. I need a permanent setup for Boom or Bust Season 2 to actually work how I want it to. So that's kind of making that take a bit of time. Another project I have is, none of you guys have seen this yet. I can't lift it up because there's a bunch of stuff on top of it. But this right here, can you see this? This is a Taramps HV160K. So that is 160,000 watts RMS into 0.25 ohms. And yes, it has all of the correct voltages and parts to potentially make that rated power. There are some questions I have around the parts on the board, like SimeWave02 is mentioning that the inductors probably won't be able to pass that much power without burning up. But yeah, essentially it will try and make 160,000 watts at 0.25 ohms. And in order to do so, it doesn't use 12 volt battery input, obviously. To get it to run and make power, you have to feed it with high voltage DC. So the maximum DC voltage that can accept is a 350 volts DC supply. So usually you would, like, the Taramps idea is that you parallel together a whole bunch of car batteries to get high voltage DC. But in the UK, our mains voltage is 240 volts AC. Now, when you rectify mains voltage like that, when you rectify 240 volts AC, you end up with about 315 volts DC after rectification. Now, that's pretty close to what that amp needs, eh? So by rectifying AC mains voltage, we can power up and run that big Taramps amplifier, and the limit on how much power that amp will make is not going to be down to the amplifier's limit. It's going to be down to whatever bloody mains you plug it into, essentially. So in the UK we have houses, the whole house has a 100 amp fuse. So you can do that. 100 times 240, that's going to get you 24,000 watts essentially that you could extract with a power factor of 1, which is never going to be the case. And that's another thing let's talk about. If we rectify AC mains voltage and give it to this amp that requires a DC input, depending on what frequency we play through the amplifier and what the reactive load of the sub is we're driving, the power factor could be absolutely diabolical, which means that we could actually be drawing huge amounts of current from the mains and not actually getting that much power from the amplifier, because obviously if you've got AC power coming in, AC is just, you know, it's just a voltage that's kind of rising and then going down. So if the amplifier draws current while the AC waveform is at its peak, that's great, loads and loads of power available. But if the amplifier draws current when the AC waveform is like at a low voltage point during its cycle, then there's no power there, there's no pressure, there's no voltage there, so the current is going to absolutely spike, and yeah, it's not going to do too well. So the way you get around that is, I've got a friend who lives nearby who has a garage, and he has 3-phase coming into his garage. Now 3-phase is as it describes, 3 phases of the 240 volts AC, and they are separated by, I think it's 90 degrees. So you have the 3 waveforms that are kind of, if you look at them on a scope, they kind of overlap each other, and you essentially get a peak and then a peak and then a peak. So if you rectify the 3 phases individually and parallel them after rectification at like a bunch of capacitors for smoothing, then you end up with a 320 volts DC supply that is being fed with a pretty lowish ripple AC. You know, you've got the 3 phases, so at any point there's going to be pretty much a sine wave peak at any point that you draw current with the amplifier. So that will push the power factor up quite close to 1. It won't be 1, probably like, it should be above 0.9. So that should allow us to extract huge power from that amplifier, obviously, and then the limit's just going to be whatever the 3-phase can supply. I don't know what that is, but yeah, I don't think we'll ever really reach the power limits of the amplifier, but it'll be fun to see if we can get anywhere near, like if we can get like a 80k out of that amp, or even 100k. If we can get 100k out of that amp, that'd be hilarious, just to see what it can do before it blows up. That's another project I've got going on the side. Another thing that I've got is I also picked up some of the Taramps smart chargers, the mains powered 200 amp smart chargers that have a design flaw, unfortunately, which means that they trip your house breaker or your breaker when you plug them in. It's more of an issue in the UK due to higher voltage, lower current. There's no soft start basically, so it just, imagine connecting a capacitor, obviously a rectified capacitor, straight to your mains. It's going to present a short circuit initially while the capacitor is empty, and yeah, it just trips the breaker, and when it trips the breaker it spikes the circuit, and it killed the MCU on one of these smart chargers. So I need to retrofit a soft start circuit for them. which Tarrant should have done. Paris did it. Paris have fitted a soft start circuit to their charger, so they can do it. Don't know why Tarrant didn't bother. Other projects, yeah, don't know. I've got other ideas for videos. I want to do a whole repair guide, you know, like a tutorial thing online with different categories and segments and chapters, but that's a long project, so lots of ideas I want to do in the future. Yeah, blowing an amp that size sounds horrifying. Yes, I agree. If you've got 3-phase going directly into that amp, and if the output MOSFET's short, then that's a dead short across the 3-phase supply. What's going to happen there? Big flames, who knows? Anyway, so yeah, what was I doing? I was going to be changing out the 4427 in here for this other drive IC, which is it's been rebadged, remarked as C2, which is from one of those Chinese clone amps. I can't remember if they use a 4427 or if they use something else. But let's just, before we change it, obviously we need to take a reference. What currently is the idle current draw of this amplifier with its current driver. So we're going to knock the voltage on the power supply down to 9 volts, which is going to prevent any of the it's going to, well, let's just go, maybe it's going for 9.5. So we're going to go 9.5, and that's going to prevent the regulation circuit from working. So that's going to mean that the power supply is going full duty. So let's probe the power supply over here. Let's probe the rail voltage, just get that back up to speed. Alright, here we go. So we are powered up and locked in. We have 146 volts on the rail. We have Class D switching. And this is what the power supply looks like. If I zoom in here. So a great big spike on the power supply, and we have 11.3. Okay, so let's remember this. We have 11.3 amps of idle current draw at 9.5 volts worth of input. So let's not change anything. Let's just turn the power supply off. And let's change the driver here for this C2 marked driver, and let's see whether the current draw changes. So if the idle current draw does change, then we know that the problem with the power supply is dead time related. If the current draw doesn't change, then it's either that these two chips don't impact the dead time and it's still dead time related, or it's that the switching frequency of the SMPS is incorrect. So sub Dynaman, yes, exactly. In that Taramps, there is no switch mode power supply. The 350 volts DC that comes in is sent directly to the output FETs as rail voltage. I don't actually know if this driver is healthy. This is one that I've obviously taken from one of these Chinese sound digital clones. I don't actually know if it works, so I guess we'll find out. RTS, I think you mean in parallel. Putting a diode in series with the 10 ohm resistor isn't gonna help. What I want to do is to obviously fit a high value gate resistor like a 47 or maybe even 100 ohm, and then parallel a diode across it so it turns off quick and turns on slow. That should widen the dead time gap a little bit. A high voltage alternator would be pretty cool. Like if you had a car, if your car alternator was outputting, say, 100 volts, if you could get 100 volts, 150 volts from your alternator, and then yeah, like I don't know of any 100 volt batteries. That's the thing. Yeah, you could series together a bunch of cells to make, but then that's kind of long. How many lithium cells, like sort of 18650s, would you have to parallel series to get to 100 volts? They're what? Are they 2.3, 2.4 volts? Are they? Are they 1 point something? What are they? I've got tons of them here. 3.6. So 100 divided by 3.6. So how many would you need? You'd need 27. Oh, that's not too bad. 27 series 18650s, for example. I'm not suggesting that they're the best solution for that, but if you wanted to use 18650s, 27 of them in series, and yeah, 100 volt alternator. Then you could run a Class D amplifier section directly from that. Did this on a problematic clone and it fixed it. I'm not really understanding though what the idea behind a diode in series with the gate resistor is. So obviously a diode is going to that wouldn't make any sense. You'd have to, so a diode obviously is going to conduct in one way and block in another way. Okay, so if you put a diode in series with the gate resistor, then let's say you put the diode the way round where it lets the voltage into the gate but doesn't let it out, then you're going to have your MOSFET turn on and then just never turn off, so it's going to explode. If you fit the diode the other way round where it blocks the incoming voltage, then your drive circuit's just never going to hang on a second, there's someone at my front door. But yeah, just think about that for a minute. I think you mean parallel. Alright, sorry about that. I just had somebody at the front door. So yeah. How's it going, guys? If you just joined, wondering where I was, there was somebody at my front door, apologies. Yeah. Series in series with the gate resistor makes no sense. In parallel with the gate resistor, makes sense. I guarantee it wouldn't work. It wouldn't work. Oh no, not series with the gate resistor. What do you mean then, buddy? It's acting like the pull down transistor, but much faster. So it's allowing voltage to dissipate to ground. That doesn't make sense either, because obviously if you have the voltage coming through the gate resistor, okay. Oh, do you mean it's... No, because it doesn't make sense either. So if the voltage is able to see ground through the diode, then it's just going to pull the voltage down to ground, and the MOSFET's not going to get any gate drive. You might get like 0.8 volts. The driver has two sets of MOSFETs inside, one pull up, one for pull down. Yep. But having a diode do that, the reason that there's MOSFETs inside the driver for pull up and pull down is because they need to be controlled as to when they turn on and turn off. If you just have a diode like to ground at the gate, then that's just going to sync all of the gate drive voltage to ground all the time, even when you don't want it to. So it's not making sense to me. Maybe I'm not understanding what you're talking about there, but it's not making any sense to me. What you want is a diode in parallel with the gate resistor so that it's slow to turn on and quick to turn off. That will then give you more dead time by way of force like that. Alright, so we fitted this random driver that I found in the drawer just to see whether that changes the idle current. So we haven't changed the voltage here, 9.5 volts. So we had, what did we have? 11.3. Can anybody remember? I think it was 11.3 amps of idle current with 9.5 volts in there. So I'm just going to bump it up to 12 volts for a second just to get the rail built nice and quick again, because it takes bloody ages on this. Okay, that driver seems to work. There we go. Let's go back down to 9.5. Okay, wait for that rail voltage to sink down. Let's have a look at the... Okay, so we still have that massive spike. So although we still have the big spike, the current draw is actually less. So yes, I do believe that this is dead time related. So this driver that I fitted will have slightly different characteristics to the original one, and it seems that it allows for a little bit more dead time. It's a bit slower than the original one. So we only have 10.1, 10.2 amps of idle current draw with this new driver. Okay, well let's leave that in place then, and let's combine that driver with some modifications to the drive circuit by fitting higher value gate resistors and some 4148 diodes in parallel with the gates to slow that whole thing down. So basically, RTS, I understand what you're saying now. So the resistors there for limiting the current, but that's still a very bad way of doing it, because you're still then at all times allowing current to sink from the gate drive to ground. By putting the diode in parallel with the gate resistor, so obviously think about this. The driver, okay, has a MOS or transistor for sending the voltage to the gate, and then another one for pulling it to ground, and they alternate. Okay, so when the drive tells the FET to turn off, the transistor or MOSFET inside the drive IC opens up, giving that current that is on the gate a very, very quick pathway to ground. Now obviously if you've got a gate resistor, that current has got to go through the gate resistor first, quite slowly, to ground through the driver. If you want a quicker path, if you want the MOSFET to turn off quicker, then obviously going through a diode instead of having to go through the resistor is a much faster way to ground. By connecting the diode fixed to ground, like you're saying here, at all times, is really bad, because it's going to go, the voltage on the gate is going to go to ground through the MOSFET driver anyway during the off phase of that waveform. So you might as well just have the diode in parallel with the gate resistor so it can bypass the gate and go to ground quickly through the driver. Having the diode with a resistor in series to ground at all times, you're basically just creating a voltage divider. So all you're doing really there is you're just limiting the amount of voltage that is being sent to the MOSFET initially anyway. It's just going to be working like a voltage divider rather than actually be allowing that voltage to bypass the gate resistor. By putting a resistor in series with the diode, you're kind of ruining the whole point of having a diode there, having a quick pathway to ground for it to turn off. So yeah, I really don't like. I know that you said that improved it for you. Yeah, maybe it tweaked the characteristics a little bit enough that it kind of made it a bit better. But I would strongly recommend against that, and instead put the diode in parallel with your gate resistor. Morning, Sam speaking. How can I help? Bye. That was just an inquiry for a JBL GTO 14001 that works but doesn't seem to make any power and cuts out, so I suspect that's a snapped terminal joint on the PCB because they're very known for that. Yeah, so that's cool. I'm pretty sure that we've confirmed now that the issue is dead time related. So what we need to do then is we need to not ruin my power supply camera by accidentally knocking it. We need to change all of the gate resistors and fit some 4148s in parallel with them. So that's what we're going to do now. Now, what do you reckon, guys? This currently has 10 ohm gate resistors. Now, these power supply MOSFETs are probably going to be pretty big boys. So I don't think going all the way to 100 ohms is going to be too wise. I think that might be a bit too slow. I'm thinking maybe 47 ohms. Actually, you know what? Maybe what I should do is I should just do the ones on one bank first and just see how it behaves. Maybe I can just do this bank first and just have a look at the waveforms and see how it likes a 47. And then if 47 is not quite enough, then we can go to 100 if we need to, or maybe 68. Ah, what the heck? Why is this one resistor like super stuck to the board? What's going on? don't know where that one went, but okay. Right, let's refresh those pads. Is anyone missing the hat cam? Was the hat cam any good or was it too intense? I haven't had the hat cam for a bit. Can try and get it back on, but it's the wire's a little bit short actually at the minute. Can I slap it on the board somewhere where we can see what I'm doing? Maybe. Can anyone bring Chris up to speed in the live chat so I don't have to explain it again? So I've been explaining it loads this stream. I need like an automated "what are we doing today" something on the live, so that when people jump in they can get an update. Just had the delivery of tea. Lovely. Nice green tea. Love to see it. Bring back the hat cam. Alright, I'll get it reconnected. I need a long wire for it, because the wire is a bit short at the moment. So we need some 47s. We try some 47s first. What do you reckon? 47s, 100s. Maybe I just go for 100. See what that looks like. Do I even have any 100s? Hat cam was a bit weird angle for me. Never quite on the right spot. Yeah. Maybe a second fixed position camera might be better. So I've got this camera here, but the problem is, like, with this board being so big, it's very difficult to kind of put a fixed camera somewhere that's always on the action. I've got some 56s. I don't have many of those though, so I can't use those going forward. 220s, that's a bit high. I have actually seen like 270 ohm resistors being used in some of the recent amps coming out of Korea. Not that recent, they're a little bit old now, but basically it was to combat the that's from 200s. It was to combat 150s. That might work. Combat the high frequency noise, EMF, I think, whatever. Yeah, it was to basically prevent hard switching so that it was less noisy electrically, to pass certain certifications. Here we go. Here's a whole bunch of 100s. So we could try fitting those. 101. I've got a bunch of 68. Oh no, that's 680s. That's too high. That's too high. Okay, let's try 100 ohms with a paralleled 4148. So Chris, basically, if you're still here, this is an amplifier that has been made in Korea, which is a Korean clone of the sound digital circuit. Usually you get Chinese clones. The Chinese have been cloning the circuit for years now, but this is a Korean clone, and they've done a really bad job. It has three main design flaws. First design flaw was that it drew current from the car battery even when the amplifier was off. Fixed that. Second issue was it had a really strange way of regulating the rail voltage at two separate points depending on your input voltage. So it regulated at 151 volts of rail under 13.5 volts. When you went above 13.5 volts, it then regulated the rail voltage to 195 volts, which seems backwards. I explained it in my previous stream in quite great detail, but essentially it would just cause unnecessary clipping. You know, like, the whole point of a regulated power supply is that you regulate the rail voltage at a point where the amplifier can try and make the most power that it can regardless of your input voltage. Stepping the rail down when you go below a threshold of input voltage makes no sense at all, and it's just going to lead to issues. I've only just been brought this tea, so it's just freshly made. I'm glad that whatever you did fixed the amp RTS. Are you talking about output section or power supply? Ceiling cam. Well, that's essentially kind of what this is. It's not quite on the ceiling, but it's, you know, up high. Let's try some different positions for this camera. So this would be like hat cam vibes. So that's on me head. I feel like that's always, like, you know, quite a good perspective of what I'm doing. I can put it here, which is very similar to the overhead cam. Wires in the way. Sorry for the nauseous, dizzy vibes. Yeah, I could put it like here as an overview cam, but it's very kind of similar to what I've already got. Can have it on the side up here maybe. Loop that round. But that doesn't really show you much, does it? What else we got? I feel like having this handheld cam is really useful for times when I want to sort of really get up close and be like, oh yeah, look, so this is what I'm currently doing, or whatever. It kind of gets you a really close up view, because this overhead cam up here really isn't the greatest resolution. And so you can't really see stuff super well. But having a handheld camera actually is quite nice. I've definitely turned the brightness up too much though. It's completely blown out, isn't it? So yeah, still working on this. Yeah, we're just kind of working our way through the 3 main design flaws. We fixed 2 of them already. We're just on the power supply one now, last one, and we've figured out that the issue does appear to be dead time related. So I'm going to pull myself out 4 100 ohm resistors like this. And let's put these other 10s away somewhere safe so they don't short out something on the board. Let's get these soldered in. Just give you back this camera actually, why not? To get it to kind of stay upright somehow to show you what I'm doing. There's one. Hand cam. I did actually trial. I experimented with a soldering iron cam one time. And that actually looked really cool, but it was just very awkward to use. It was very bulky on the soldering iron and didn't stay in place, but it did look really cool. Okay, so now they're all fitted, 100 ohms. We need to put some solder blobs on the top of them so that we can mount a 4148 diode on the top. Chest cam. Yeah, maybe a chest cam's a good idea, like a body cam, because then it wouldn't be moving around so much like the hat cam does. I wonder if I can strap something onto my chest, that might work. Right, sweet. So now let's grab some. Now let's grab a cookie. And now we have some 4148s, which are going to be in parallel with the gate. And we're going to block incoming, and we're going to sync outgoing. Now I'm going to have to move the camera out of the way a bit here because it's kind of in the way still. What does that look like? You can't really see anything at all there, can you? No, I just have to go here. That's two fitted. So this modification, doing this to all of these, definitely is going to take a while, so not the most ideal thing. There's three, and last one. Okay, 4. So provided I have fitted those diodes all the correct way around, it looks kind of janky because the diodes don't really want to sit on top of the resistors, they just kind of want to fall off to the side. But I don't mind that so much, like it doesn't look amazing. I'll obviously clean the flux up. Will it focus that close? Yeah, you can see it doesn't oh man. Will you get any brighter? No. It doesn't look amazing. The diodes are just kind of off to the side of the resistors, like that, but they are connected and everything is connected. So it's just a test of theory to see whether this is going to change the behaviour at all of that bank of power supply FETs on that transformer. So let's power it up and have a look and see what it looks like on the scope. So we're looking for a decrease in idle current, and we're looking for a lack of spikes on the output here, and we also want the gate drive waveform to still look kind of alright. So let's just get the back powered up again. Just increase the voltage a bit so that it starts up. Okay, there we go. Back down to 9.5, which is where we were at before for calibrating this. Okay, the gate waveforms actually look not too bad there, just on the kind of health check pulses. Okay, so we still have a bit of a spike there. We are increasing, we're rising 9.5, right, so we've got 10, what did we have before? I might have to scroll back through the stream. So we've still got a bit of a spike there. 10, 20, 30, we've still got a bit of a spike there. But is the spike less than on a bank that doesn't have that mod? Yes, it is. So you see, this is a bank that doesn't have the mod. So see how the spike is like miles off the screen there, okay? So yeah, this is a bank without the mod, and this is a bank with the mod. Way less spike. Bank with the mod, bank without the mod. So that's definitely helped. The gate waveform looks bloody fantastic actually. You know what? I think we could go much higher than 100 ohms. I think we could go like 270, and I think that would actually improve this further. So I think we're going to fit something like, you know, 270 ohm gates with the parallel diode, and I think that will reduce the spike even further. And yeah, that'll help. Yeah, Chris, 10 amps idle, but it was worse. Before we did any mods, it was up at like 11.8, and that's because of this issue. That's yes, it was. I think it was 11.8 was where it was before, and that's with 9.5 volts worth of input. When it wasn't voltage regulating, when it went up to 12 volts, it was trying to draw like 20 amps on idle, and that's because of this cross conduction issue, because there's not enough dead time in the MCU. So that's what we're trying to fix. But I'm very pleased with that. The 100 ohms looks great on the gate drive, so I think I will fit some, yeah, some bigger ones, some 270s. So let's see, what do I have that's a bit bigger? I have 200s. You know what? Even 360s or something would probably be fine and would really help. So I'm going to see what I've got that's around that kind of mark. So 200s, yes, we could use. Can't use thousands. Can't use thousands. That's way too high. 56 is too low. These are too small. That's too high. 150 ohms is not quite enough. I want more than that. That's too small, probably. That's 150 anyway. That's way too high. 330. I'm curious. Would 330 work, or would that be too high? I think I might try it, you know. Let's try 330 ohm gates, shall we? On this bank, just to see what the gate waveforms look like and see if the current draw looks any different. I just need some tweezers. You know what I might do? I might just have the diode, rather than the diode going across the gate, I might just have it going from the actual leg to the pad. That might be much easier, because it's kind of a bit of a faff. So block coming in, down coming out. Yes, I think this camera angle might be the one. Just like, you know, having a free hand cam that I can just move around. That might be the way forward, I think. There we go, that diode's nicely in. Move that one. Bloody hell. Right, one of those diodes is underneath this transformer, so just get that out. Yeah, I'll use some flux when, at the moment I'm removing parts, so I don't need flux to remove parts, but I need flux to fit parts. So when we come to fit these 330 ohm resistors in a minute, that's when I'll drop some flux on. Right, so we're blocking that way. So please behave and just tack on there for a minute, just while I get the other resistors out, will ya? There we go. Thank you very much. Right, so now we drop some flux. But I don't use tons of flux because this stuff's bloody expensive. And I like to try and make it last as long as possible. So, 330 ohms. What are we going to do with 330 ohm resistors? Let's see, shall we? And just before I fit these, I'm just going to, with the big main iron, I'm just going to tack on the diodes at the gate legs, because that will stop them moving around. Oh man, I really hate that that these use these kind of MOSFET leg isolator things, these little heat shrinks. Get out of here, man. I'm trying to solder to you. I don't actually need to solder to the leg, I just need to solder to the pad, but the leg's kind of getting in the way, stopping me from being able to heat the pad up enough. There we go, that's worked. Can I do the same to this one? There we go. Okay, lovely stuff. Now we do the gates. Alright, that's the last 330 gates, so let's just make sure that they're all connected to the diodes at the back. And then let's see whether 330s are happy here. Alright, so yeah, let's get ourselves powered up. Move those out of the way for a sec. There's the 330s. Let's put these 100s in the drawer. So yeah, we're looking for even less spikes than we had before. Okay, let's just get this powered up to full whack. Okay, there we go, we're all powered up. We have class D switching, yep. So let's have a look at the waveforms on here. So we still have a little bit of spiking, and we're down at 10 amps. So that's basically the same as what we had with 100 ohms, 100 ohm gates. Let's have a look at the gate waveform. So that looks a little bit too curvy for me. It's not bad, it's still good, it's still fine. But given that we haven't really made any improvements over the 100 ohm gates in terms of spikiness, so that's the modded circuit, and this is the unmodded bank. They're kind of the same. So I think we just go back to 100 ohm gates across all of these rather than the 330s, and do all banks with 100s, and that should be sorted. Do you have contact with Loudfear? Yeah, man, I chat to him here and there. He's very busy though with his voltmeters and wattmeters and stuff. I've actually got one of his voltmeters here. I've just never connected it up because I wanted to do like a cool video on it, or like integrate it somehow really nicely into my setup. But I just can't think how to do it justice, and so it's kind of just been left. I feel a bit bad about it. I'm going to integrate it into something. It will be part of some build somewhere, sometime. But I appreciate that it won't necessarily be fresh and new at that point. So yeah, I'm happy with the 330s do work fine, but I think the 100 ohm gates, they're a little bit bigger in size, which does help the diode to kind of parallel with them, which is nice. And the gate waveform did look a little bit nicer with the 100s. So I think we're going to remove the 330s and just stick with the 100 ohm gates, and we're going to do that for all banks. So that's going to take me a hot minute. So we can have some chats if you like, guys. We'll do some Q&A if you like while I'm doing this, because otherwise I'm just going to be sitting here soldering for probably like 15 minutes or something. If you had any questions or any random stuff you want to talk about, it doesn't even have to be audio related, anything you want to talk about. Let's get a conversation going to keep the stream pumping while I'm doing this. Robert says, I'm driving to the reality YouTuber documentary area of Pennsylvania. So I don't know about that. What's the reality YouTuber documentary area? Is that just like a place that a lot of people go to make content? Or is that where there's a lot of content creators live? Are you going there for YouTube reasons or just for other Pennsylvania reasons? don't like how close this one is to the ground trace of that transformer. So let's flux that one up and get rid of that big blob. Just jumped in. 1 degrees Fahrenheit in Iowa. What's the weather like over there? Yeah, it's about 3 degrees Celsius. I don't do Fahrenheit, sorry bro. I know that 1 degrees Fahrenheit is absolutely freezing. I know that must be bloody cold as heck. But yeah, I currently have about 3 degrees Celsius here in the UK, which I don't think is anywhere near as bad as what you're experiencing. But it's still not warm enough for me. I'm a hot weather person. Man don't like the cold. Everyone started doing Kensington area documentaries for the last few years. Going to pick up my friend and scoop him out. Oh, fair play, man. Hope you have a great day. Sam, did you say that we can talk about anything else too? Yeah, sure, man. Of course. Just do what you want, man. Chat about anything. 60-mile-an-hour winds predicted for that area today. Oh, that's pretty rough. 60 mile an hour is pretty fast. Shouldn't be too bad though. You shouldn't have too many trees down, but it can bring some stuff down. I think the most recent storm we had in the UK was 90 mile an hour, and me personally, I didn't get any damage or anything here. It was fine, but I know that there were damages in various different places, but I was alright here. The UK isn't really historically known for its dramatic weather. Like, the UK is always kind of known for just having very boring weather. Like, it's never too extreme, you know. It's like, it's kind of a bit warm or it's like a bit cold, you know. It's kind of mostly wet and stuff. But in recent years, we've been having more kind of extremes of weather. So we've been having hotter summers and more colder winters, more storm weathery wind and stuff. It's very windy up where I am actually a lot of the time. Get loads of wind up this way, which is a shame. Don't like the wind. The wind is probably one of my least favourite weathers. I don't even mind the rain so much. I just hate it when it's so windy. It's just kind of abrasive on your entire self. I don't ever want to do anything when it's like so windy outside. You know what I'm wondering actually? I'm wondering whether diodes across the 10 ohm gate resistors would actually be enough on their own without needing the hundreds. I wonder whether me fitting the hundreds is just kind of pointless, and whether 4148s across the 10s would actually be good enough to get this out of cross conduction. Don't really know. Hi from Norway. Long time since I've been able to catch one of you live. Currently at work, doing power measurements on ultrasound. Nice, man. That sounds interesting. Hope you have a great day. 3 degrees Celsius is 37 Fahrenheit. Wow. Yeah, that's mad. That must be very cold for you. I settled for increased port area on my sub today. Nice. Bit louder, higher tuned. I did ask you a question earlier to do with politics. I didn't see that, sorry bro. Feel free to ask it again, but I'm not politics. I have no idea about politics, so I might not be able to answer you very well. I work in most weather. Summer rain wasn't bad. Yeah, I don't mind the rain so much really. BMW that has a Harman Kardon system with an under-seat 8-inch sub. Would you say upgrading them and power them externally? So the limitation you're going to have with an under chair sub is just going to be like the box volume, right? So the only way to get like actually good output from a very, very small box is either you have to play high frequencies or a passive radiator. So what I would probably do in that instance, depends what kind of frequencies. Under seat subs, if they are your only subs, then sure, okay. If they're your only subs and nothing else, then I would probably just rip them out and I'd probably work out what the biggest boxy type thing I can get under the seat is. I then build that size of box either out of wood or maybe 3D print it or something like that. And then I would, obviously before building it, but I'd work out a passive radiator setup. So what kind of driver and passive rad can I fit in this box on the surface space that I've got? You know, it might be a 4-inch driver with an 8-inch passive radiator, for example. It might be if I can fit a 6-inch shallow driver in there with a 6-inch driver with like an 8-inch passive. If I can fit a 10-inch passive radiator, like a really slim one, that would be quite nice. But I doubt it if it under seats. So now, yeah, the 10 ohms. I guess I'm just going to remove all the 10 ohms. I'm just going to drop the hundreds in because I've started doing that now. How much space does a passive radiator actually save? So with passive radiators, the box volume is, obviously it matters a little bit, but it's not as critical. It doesn't really matter as much. It will obviously impact the result in some way, but the whole thing about a passive radiator is the same as a port. Passive radiator box is the same as a ported box. So with a ported box, you have essentially infinite amount of displacement. So the way you need to think about a ported box is that at and around tuning frequency, the port becomes the driver, okay? The port becomes the cone. So what you're doing is at tuning frequencies, you're taking energy that you're sending into the cone and you're levering that. So you're basically like a kind of pulley system. You're putting energy into the coil, and the subwoofer driver is not moving much, but all of that energy that you're putting into trying to move the cone is actually going into moving the port. Okay, so the port takes over and becomes the driver. Now the benefit of that is that the port doesn't have a mechanical limit of displacement. Yeah, so the port can basically move in and out as far as it likes within the constraints of the airflow and the frequency you're playing before it chokes. Okay, so having a ported box is like having a driver that has, you know, like 10-20 inches of X-Max. You know what I'm saying? So that's the benefit of ported boxes. It allows you to displace way more air than the cone ever physically could by using spring resonance taking over from the cone, like that. But in order for that to work, and in order for you to tune that port to a specific frequency, it depends on, and you're tied into the box volume and the port area and length. So those three things will tune the port to a specific frequency: box volume, area, and length. Now, if you are limited on one of those, so let's say you're limited on box volume, like you just can't make the box big enough to tune it to the frequency that you want. Well, what you can do is you can exchange your port for a passive radiator, which is the same thing, but the passive radiator is basically a port that doesn't rely on the box volume being a factor for tuning. You swap the box volume for mass, for passive radiator mass. So instead of needing a big box or a certain size of box, you can basically make the box really, really small, because the volume doesn't matter anymore, and the passive radiator, the tuning frequency now, instead of being based on the volume, is based on the mass of the passive radiator. So the volume isn't really much of an important factor. I mean, it will change it, obviously. It will change the characteristics of how the box plays, but you don't have to worry too much about the box volume like you do with a ported box, or like you do with a sealed box. You can make it really small, and you can tune your passive radiator to a specific frequency based on its mass, and you basically got a really tiny ported box. But obviously the limitation with the passive radiator is a passive radiator does have a mechanical limit. It does have a mechanical limit to how much it can move. So you've kind of lost the great thing about ported boxes in being able to displace as much air as you kind of like, because the port doesn't have a physical limit. Passive radiator does have a physical limit, so that's a trade-off. But having a passive radiator small box is going to be louder and definitely hit lower than having a small sealed box, because you're levering that energy you're putting into the driver to displace air from the passive radiator. So yeah, with a passive radiator design, you could definitely get under 50 Hertz for sure. You could knock right down to 30 Hertz. The only issue you might have is positioning. So obviously you're going to have the subs under your seat, and where you're sitting there in relation to the sub might actually be in a kind of dead spot for lower frequencies like 30 Hertz to actually build, and for you to be sitting in a peak at 30 Hertz. Yeah, it might work, it might not sound great. With under seat subs at 30 Hertz, you might actually get great 30 Hertz in the back seats, possibly, and you might get great 30 Hertz in the boot, or maybe right up against the dash. But when you're sitting above the sub, like directly in line with it, depending on how the acoustics in the cabin are and how the standing waves are building, you might actually be sitting in a null. So that's something to think about, or you might need to test that. And if that's the case, instead of having under seat subs, you might want to instead go for like footwell subs in the footwells, passenger footwell for example. That might be better. Good morning, Strictly Amps. Good to see you, buddy. Have any of you guys heard of Hammertech? No, I've heard of the name before, but I don't know what it is. My brother owns a Yaris. Do you have any good idea how I should fit two 6.5 inch drivers? So you can do some clever stuff in the boot that doesn't actually take up space. You can make a false floor, and you can build a T-line that is obviously a long folded line, but that's not very tall. So basically it just acts like a false floor. So you still have your kind of whole width and depth of the boot, just with a little bit less height. You might lose like 6 inches of boot height, but you'd have a couple of 6.5s in a T-line, and that would be pretty cool. There's a video for best sub positioning in the car on YouTube. There is, but unfortunately, you can't use that for every car. Every car is very, very different in terms of best positioning for sub, for the various different frequencies. Each car will have different nulls and peaks at different frequencies in the cabin. For example, in my Proton, what I found was if I wanted the bass to be extremely fast, tight, accurate, like higher bass, like from maybe 45 hertz and up, like 40 hertz and up, if I wanted those frequencies to be strong, potent, accurate, like sounding great, and if I wanted to play rock music, like metal and stuff, and have the kick drums just be like insane, then I needed to fire the subs up and have the port firing up, and the port needed to be just behind the back seat, so basically further forward towards the front of the car. Probably firing the subs forward towards the front of the car and having the port firing towards the car also would have been great with the back seats down. But in that orientation, the low frequencies were very lacking. Turn the sub box the other way around, having the subs firing at the tailgate and having the port firing at the tailgate, or like down in the corner right at the back of the vehicle, the lows were suddenly immense, very, very potent low frequencies, but the higher frequencies and the higher bass and the kick drums from rock metal and stuff like that, they weren't anywhere near as good. Okay, so that's all of the 10 ohm gate resistors removed. So now I need to just freshen up the pads ready for the hundreds. So the Proton is a hatchback, but it's not a flat hatchback. It's like a slopey down to the back, but it's not a saloon with like a saloon boot. It is a hatchback, but it's not like a Eurobox flat back. It's like slopes down. Okay, now we need the hundreds. Where have I put the hundreds? 200s there, 330s there. There we go, there's the hundreds. So I'm going to need a whole bunch of these, aren't I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 20 of these. Shee! A little bit more flux, I think, will help out massively. Then I've got to do the same thing again to fit the bloody diodes. quite a long modification, this. Takes a bit of time. How's it going, John? Good to see you, buddy. I wondered if that creates like a horn effect. Yeah, it will a little bit. Not really. The horn kind of expansion and size wouldn't be correct for the frequencies you're playing, so it wouldn't really have a horn effect as such, but it will help to channel the pressure forward, I guess, in some way. Toyota GT86 makes a Handley FLH shape if you put steel drivers in the rear quarter panels. That's pretty interesting. My younger brother actually has a GT86, so I might suggest that to him. My other option I thought of, as I have a coupe, run a 12-inch infinite baffle on the rear shelf. Yeah, that would sound great, honestly. Like, obviously it wouldn't be as good as having it in a box, supported box, but compared to other options, that's probably going to be a best bet for sure. Could you even do a 15 on the shelf? Would a 15 fit on the shelf? Good morning, D. Hermison. How's it going, buddy? Are you going to take the rear window out to make the subwoofer baffle into the rear shelf? Eh? Yeah, I'm not sure. I don't think that question is to me. I'm not sure what that means. Heck, they are smaller than the little 603 LEDs. Yeah, these are pretty small. William, yes, definitely. I definitely will, William. Hopefully not too long now. Just logistics that I need to sort out for that. get the nose cam. How do you find the nose cam? You in England, new to the channel. I must say you do some darn good work, bud. Oh man, thank you very much, dear. I appreciate the kind words there, my friend. Yes, I'm in the UK, up north. Yeah, pretty cool. Don't mind it. Don't love it, don't hate it. Does the job. But no, I appreciate the kind words there, my friend. And I hope you're having a great day, and I hope you enjoy the channel. Yeah, my hot air gun does have a very long nozzle. I'll tell you what, this was a game changer. I highly recommend that you grab one of these from eBay or something. They're just cheap, like, long nozzles. They're a bit leaky. Like, there's a lot of air pissing out of the joint here. You have to turn your pressure up a bit as well to get the air through faster while it's still hot. But yeah, this hot, long nozzle is a game changer. I highly recommend. Made life so much easier for me with the hot air gun. Alright, 3 more to go, and then we just got to do the diodes. Now, how much current draw do you think we will have lost? That's the question. So we started off with this amplifier at 9.5 volts worth of input, trying to draw 11.8 amps at idle. How much idle current are we going to see with this modification complete, do you think? I'm thinking maybe like 7 amps, 6.5 to 7 amps probably would be fine. We do still have some cross conduction on the power supply. Like we're not going to be able to get rid of it completely because the MCU has been programmed wrong, and we can't really do much about that without, you know, being able to program a new one, reverse engineer the firmware, all that jazz. This is long. So we're always going to have a little bit of cross conduction on the power supply, which is a shame. But yeah, I'm hoping that we can bring the idle current down a fair bit because it was ridiculous before. I mean, it says 5 amps. I would like that. Do you prefer soldering speaker wire onto speaker terminals or spades in a door, for example? I find soldering like in the vehicle like a bit annoying because I don't have a a gas soldering iron really. So for my own personal installs, I'd probably just terminal, spade terminal. I would rather solder though, so if I had a good battery powered or something, probably not gas soldering irons are a pain in the butt. Probably if I had like a nice lithium powered soldering iron, then I'd just solder them for sure. But I don't have one. Actually, that's something I should put on my next birthday list or something. Actually, it's a good idea that battery powered soldering iron. That'd be super useful, because there's a lot of things I think, oh, I'll just solder that, and I've either got to bring it into the workshop, or if I can't bring it into the workshop, I've got to bring my massive soldering station, like get it out of the workshop, disconnect it all along. Right, that's all the resistors. So now we just got to do the same for the diodes. Fit all of those in. So a bit more flux. And for the diodes, it's even more annoying because we have to super pay attention to the orientation and make sure that the orientation is correct. So, yeah, we're going to need we're going to need 20 of these as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Ah, spring terminals, yeah, that's pretty cool. That would be handy. Man, I wish you were in the US, says Chris. What do you need help with, man? I know that there'd be tons of work for me in the US. There's like there's a lack of repair techs in the States. There are some great ones, but the ones that are there are like super backed up because there's more amps than there are repair techs. So I would have a ton of work in the States, but I don't really want to live in the States, so I like being here. Here's fine. Man, this one's being really annoying. DC 9K and Twisted Sound 8.5K. There's definitely some good techs in the States that could sort those for you, my friend. I actually hate working on those massive Koreans now. the rail voltage is just so high. I hate it. And when they go bang, they're like boom, big boom. So yeah, I'm not going to get into politics because I don't know anything about it. I don't care. I just want to get on with my life. Are you using a microscope or just the camera? So at the moment I'm just using my eyes. I'm just looking down on the board like this. I do have a microscope that I use for some bits that are really tiny, but this stuff isn't so small that I can't just see it with my eyes. Also, I don't have a big enough microscope that's going to get down over the board high enough at the moment. So yeah, these parts really aren't that small. They're quite big in comparison to some stuff like motherboards and games consoles and stuff that are much smaller. This stuff ain't too bad. Oh my god. Okay, I think that's all the diodes done on one side of the board, so now I've got to go ahead and do the other side. This is fiddly stuff and takes a little while to do. My Amplifier guy retired, but he told me the website to order everything from. Yeah, you should probably do it. You could be, you'll be able to do it. You'll be alright. So now we're going to move on to the other side. So you should be able to see a bit easier because the transformer's not in the way. I'll zoom in a little better. My head's probably going to get in the way though. My next tool will be a battery powered nail gun. Sounds interesting. I can't think of any times when I've needed a nail gun, personally. If you build a lot of boxes, maybe that would be useful. What solder do you use? I use 6040 tin lead. I don't like the lead free. Almost done. Just a couple more. Right, last one, and then we just need to go along them with the main soldering iron, which will just make sure that they're all definitely super well connected. One of the diodes actually went under the transformer, so I'm just going to try and knock that out. Kind of blew under there. It hasn't come out from the transformer, so maybe it's kind of stuck there with flux, in which case no worries, you can stay there. Oh wait, no, I see it. Come on. So I'm having a dilemma choosing how I want to incorporate lithium into my install with an AGM starter isolator DC. Wait, what? Just replace your normal battery with a lithium one, if you like. You don't need to do all this complicated chargers and DC to DC, all this stuff. Yeah, just take your AGM battery out. If you're running just a single lithium battery and that's what you want to use, run that up front. Yeah, well, I'm not seeing this diode. So I guess that's not going to cause any issues, so I just need one more now and then we're done. We can just go around with the iron and just make sure that they're all properly connected, and then it's good to go. Alright, well that one has wanted to sit on top, which is unusual. Sweet, so let's go around with the iron and just make sure that they are all very, very nicely connected. And then we can find out how much current draw we have saved. I'm And we can also just to make sure that I fitted the diodes all the correct way around, which we'll be able to tell when we power it up and have a look at all the gate waveforms. So if you're going to do battery delete and have lithium, probably just run the lithium in the boot, in the trunk, in the back, and run some wires for your starter motor and stuff up to the front where the original battery was. So delete front battery, run lithium in the rear. Alright, so moment of truth then, find out how many diodes I've put backwards and find out how much current draw we've saved. Make sure there's nothing floating around in there. Okay, so current draw previously was 11.8 amps at idle with 9.5 volts worth of input to the amplifier. So as long as I see below like 8 amps, that's a decent saving there. That's fine. So let's put some power in. So first of all, we get this powered up. Go back down to 9.5. Okay, unfortunately we have quite a bit of current draw there, so it's possible that I have fitted one or more of the diodes backwards perhaps. So let's have a look and see what we get. Let's have a look. So we are going to be probing each bank of these power supply FETs and just seeing what the waveform looks like and seeing where I've gone a bit wrong. Okay, so that one looks okay. That one looks okay. That one's okay. That one's okay. That one's very, very big spikes. Okay, so let's have a look. What's the gate waveform look like here? Okay, very, very big spikes on that one. Not big spikes on that one, but we do have big spikes on that one. So does the gate waveform look different? No, the gate waveform looks the same. 12.6 amps. Jesus. So I've actually kind of made it worse. That's not good. Very strange. It's really interesting because when we initially did this bank over here, this spike was like really nice and small, but now it's big again. And we have quite a lot of current draw, and we have quite a lot of heat on the heatsink here. Oh man. So that hasn't really helped, has it? How frustrating. How frustrating. All of the signs were pointing towards that being a good solution. So we changed the driver for one that had slightly higher dead time. That reduced the current draw. We fitted one bank of this, one transformer bank with 100 ohm gates and parallel 4148s. And that reduced the current draw from like 11 point something to 10 point something. So we're like, okay, cool, we're on the right track. We just need to do this with the rest of them now, and that should solve it. But actually we've gone the other way. Bit confused about that. Let's just check every single one of these gates just to see if there's one somewhere that's pretty bad. Okay, that's got a nice sharp turn off. That's got a nice sharp turn off. Nice sharp turn off. Nice sharp turn off. Yep, nice sharp turn off. Yep. Ah, hang on a minute. Right, this gate doesn't appear to be connected to anything. Right, okay, that might be a problem. This one here is not getting any gate drive. Okay, let's resolve that. Must just be that it's not quite on the pad, because these are much bigger resistors than the pads will allow. So most of them are connected fine, but you can get ones where they're just a bit disconnected. So let's use the multimeter and just confirm. So we have gate connection on. So let's go for these banks here first. So we should see about 200 and something on the meter. Yeah, so 273 is what we're looking for. So 273 up, 273 up. That one is the other banks, that's fine. 273, 273. Okay, great. So now let's do the other bank. 273. Skip. 273. 273. Right, which one didn't have any gate drive on it then? It was one of these. It was one of yours. Right, that one has. That one has. This one hasn't. Okay. Q14 hasn't. So let's just refresh Q14. Okay, that's refreshed, so let's have a look. Q14. Do we now get gate drive? Yeah, we do. Okay, so that's that one fixed. That one's got gate drive. That one's got... this one here has what looks like very slopey off gate drive. Okay. That's got nice and sharp gate drive on the off. That's got very slopey. So it's possible that either this diode isn't connected or it's backwards. Looks like it might not be connected actually. Yep, that one's not quite connected properly very well, so let's just connect that one up. Okay. So now let's check that. That should be nice and smooth now, that one. So, sharp off on the gate, sharp off on the gate. Let's just make sure we're not building like excessive amounts of rail voltage. No, we're not, that's good. Sharp off on the gate, that's good. That's good. That's good. That's good. Okay, now let's move over to the other side. That's good. Right, that one's bad. This one right here. So either that's backwards or that's not fitted correctly. Have a look at it under the microscope. Okay, that was fitted the correct way around, so maybe it just wasn't making a good connection. Okay, that should now be correct and sorted on that one. Let's check. Yep, nice and sharp on the off. Nice and sharp on the off. Yep, that's good. That's a good. That's a good. That's a good. 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 Good, right, so now they're absolutely all correct and all fitted very well. So now let's see whether the current draw is any better now that they're all properly fitted. Okay, that's better. So yeah, we've got 9 point, it's rising slightly. So we're down at like, yeah, 9.9, 10 amps idle current draw. The spike there is a bit bigger, but I think the spike is actually smaller than what it was before. So that's better than 11.8 amps. I'm happy with that. It's not great still, but that's the best we can do. As we saw, going up any higher on the gates didn't really help. So that's the best we can do for that. There is something we can do on the output section actually that should help reduce the current draw. So over here on the output section, for some reason, now it's probably to reduce spikes and stuff, there's actually some a couple of resistors and capacitors here. So you can see here we've got these 1 ohm resistors and capacitors, and these are basically in series. They are across, what am I trying to say? Low side drain is here with class C switching on it, goes through the 1 ohm resistor, through the capacitor to ground. So I guess that's kind of working like it's grounding like super high frequency spikes and stuff, but it actually lets quite a lot of current pass, and it causes these output FETs to heat up on idle quite a bit. I'm not a big fan of it. So what I would quite like to do is actually lift those, and what I tend to do most often is I lift those, and it massively reduces the idle current draw and it stops the output FETs from heating up on idle. So I'm just going to go and try and find my little pull down resistor so we can get rid of the rail voltage. I'm just going to lift those parts, and you'll probably see that the idle current draw goes down a fair bit more still. Okay, there we go. So if I flux these up, I'm just going to remove them, lift them off. 1 ohm in cap over there, and there's some more over this side somewhere as well. Just got to find where they are. Here they are. I'm just going to knock those off their pads, because from my experience, removing those doesn't cause any issues. The amps don't come back, they don't randomly fail. Just means that they don't quite run as hot on idle, which is good. I'm going to leave them in the board just in case, you know, they're ever needed at some point for whatever reason. These little 1 ohms. But just lifting those off, we were just up at about 10 amps idle, and this should help a bit with bringing it down a little further, I do believe. Okay, so let's see what we have now. The health check mode is so long on this, hey? It takes ages to turn on. So long. Okay, there we go. So now we're down at 9.2 amps idle. So we've lost almost a whole amp, 0.8 of an amp idle current draw just by lifting those parts. And that was a 1 ohm resistor in series with a capacitor to ground across the Class D switching. So 9.2 amps worth of idle current draw is still way too much. It's still ridiculous, but this is the best we can do without doing absolute drastic rebuilds and like swapping transformers and like reprogramming the MCU and stuff. This is the most that we can do sensibly, that's affordable for the client in this case. You know, if a company was paying me to do R&D, you know, paying me thousands and thousands of pounds to perfect this circuit, then obviously, yeah, we try all sorts of stuff. We reprogram MCUs, we try different switching frequencies, we try different transformers, la 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 la. But in this case, without having to reprogram the MCU, this is the best that we're going to get it. We have a rail regulation there of 180 volts, which is safe for the output FETs. And we have much lower current draw. Like, it's still not great, but it's still a fair bit of current draw. As you can see, 9 amps is ridiculous, but that's the best we're going to get, I think. So, guys, I hope you enjoyed this little series of getting this into the best place possible for someone to actually use and enjoy, with it being somewhat reliable. My doorbell is going off just now, so I'm going to go and answer that. Guys, thanks so much for joining. If you enjoyed the stream, feel free to like and share. Send me a message on my Bearvis Facebook page, and I'll see you next time. Goodbye.